Okay, our final keynote is Jordi from ZisK, and he's going to be talking about ZisK and distributed real-time proving. Okay, welcome to the stage, Jordi. Thank you.
So, hello everybody. I'm Jordi Baylina from ZisK. I'm gonna go straight to the point. I mean, when we started the project, our main goal was to reduce latency. That's how we started all this project. And here is, I think with this, what would be more or less a standard block, this is more or less where we are. Okay? As you see, when a block is created, then it needs to be broadcast. I mean, this is sent to the block proposer. This is broadcast. Then it needs to be signed, and at some point we get the block, and we can actually starting the proof time. Okay. Then we have the input generation. We have the executor, the witness. Then we have a challenge phase. It's computing the challenge. And then once we have this challenge, then we have the second challenge, and then we have the aggregation. And finally, we need to send this to Fproof or to the network or whatever it is. Okay. So, and this is, you see that the part, I mean, this, especially the last two parts, these are very parallelizable. So this is where you can reduce a lot, and you can compress a lot just by putting more GPUs. And of course, there are some optimization pending. The main work currently is in where I think we can still have a lot of margin to improve, is all the part. I mean, even from the beginning. I mean, all the initial states probably until the executor itself. This should be compressed. I think here we can pipeline a lot of things, and there is a lot of work there. So easily you can see that here we can still earn a couple of seconds there. So this is very much the idea, rough idea of where we are. Of course, in the aggregation part, there is still some optimizations that are pending. But I mean, currently, well, this is the server. I mean, this is the cluster that we built in Girona. This is 16 GPUs running in parallel. And yeah, this is the results that we get. I mean, this is with 24 GPUs in this case, and this is I mean, this is the average time of 647, but the interesting part is the second one. I mean, this is the time to proof. This is from the timestamp of the block until we get the proof available. So we are at already an average of 9.6 seconds, and 92% of them below 12 seconds. I mean, this is at the end what we are trying to reduce, as what we are trying to compress very much. I think we can go much better with the optimizations that we have, but yeah. Just a comment on this. The GPU, I mean, we are combining GPUs and CPUs. As you see, there is this part of execution. There is a lot of part that's running in CPU that you want to go fast. So these machines, they have a 5 gigahertz speed in the CPU, and then have the 5090s, okay, and combining and coordinating them, this is a little bit the trick altogether, okay? So this is where we are, but actually what I wanted to explain now, and I want to talk in this presentation, is about building the proof in a decentralized way. In order to do that, I need to explain a little bit how the protocol, I mean, what's the coordination? What happens? So imagine that we have let's say a coordinator, okay, and then we have a lot of workers, in general, running in different CPUs, and what messages you send. So the coordinator starts a proof, then of course it passes the input. This can be up to 15 megabytes, depending on the size of the block, but this is all the information. By the way, this is a proof, so I've seen a lot of projects, for example, going fast, there is a big trick. I send this 50 megabytes, proof is generated, 0 GPUs, 0 time, free. But the idea, the full point of the systems is to compress this 50 megabytes to something that's smaller. In our case, it's 250K. Okay? So that's important to know, that this is already a proof in there. So what you want to do is actually compress. You get this input, this 15 megabytes, Of course, this is distributed to all the means the block, okay, the block header. So this is sent to the workers. The workers actually compute a challenge. A challenge is something very small, something that's around a couple of kilobytes, okay? This is then broadcast, sent to the manager and send it back to all the computations. This is where all the computation actually happen, where the subproof or the partial proof is generated. And then all this is about 300 kilobytes, the proof. And then this is, of course, this is sent to one single aggregator that just collects if you have 24 GPUs, you can collect 24 proof and you finally aggregate. This is a very fast way. But the important part here is to see that the traffic, if you see the quantity of megabytes of coordination that's here, is very, very, very small. Workers don't talk each other too much, okay? So this is very, very useful because if these workers, instead of being in a big cluster, they are distributed, the time to build the proof would not change significantly. It should be more or less the same. And this is interesting because this allows not only to build the proof in a decentralized way, but also if you replace the coordinator with a consensus layer, you can build the proof in a distributed manner, okay? And I think this is important because, we'll see later, but one of the big problems of having a big cluster that's running, for example, Ethereum, is that what happens if this cluster stops? You say, okay, you have many. Okay, but what are the incentives to do there? So I believe more in a way where there are some incentive for the proof to be built, and this incentive goes to, let's say, to validators, to roles in the network that they have a single GPU. Okay, or there are a domestic machine in there. Okay, so how we embed. We will have a debate later. I didn't when I submitted this presentation, I didn't know that would be a debate about that. But the idea is who pays the proof? But it's not who pays the proof. What are the incentives for the prover to be generated? Okay, so there is one simple solution on that, okay? It's like you sell the validator if you submit the proof, or you are forced to submit the proof, and then you will get some reward for that. The same way that the validators get rewards for attesting or for proposing blocks, they may receive some rewards for generating the proof. The problem of this simple protocol is it's a problem that so it can happen that one single provider generates the proof, and maybe all the validators are getting from this proof because it's cheap, it's free, they're getting the proof. But what happens if these validators stops? Or what's even the worst question? Okay, so you have a backup, but then what are the incentives to run a backup if you are not getting anything out of there? Okay? So you need to, it's designing a protocol that way is not that easy, but definitely the structure of building the proof in a decentralized and that you have minimal bandwidth coordinations, this helps. So what I want to show you here is an example of what a protocol, what a decentralized, what a protocol could look like in order to build the proofs in a distributed manner. Okay, so of course you need to have provers in the network the same way that you have validators. It can be the same validators, or you can have a new role. You put 32 ethers and then you are a prover. Prover means that you have a CPU with a GPU, so you have let's say a gaming machine on there, and you will get rewards for that. Okay, so the thing is that probably randomly deterministic, the same that we have these committees and that you are selected randomly, you will be selected to do some work. Okay. This could be something like, okay, you are the chunk number 23, you need to do the chunk number 23 of of the proof. And this proof income can be you can be the chunk 23 of a ZisK proof and a chunk 23 of an SP1 proof or other proving systems in there. So you can have even a distributed way. And of course, maybe in this protocol, you would not be the only one. It can be some redundancy that can be designed in that. Okay? So once you assign what's the proof you have, well, maybe you can divide it here in 3 steps. The first step is you generate this phase where you can generate this challenge. Okay? You generate this challenge, and then you can have an incentive. Okay, if you are a prover, you put the challenge, and for the fact that you are putting the challenge, you get some reward. Of course, you want to add also some reward to the validators in order to incentivize them to include your reward, so to include your challenge in the block or in the consensus. Okay. Second stage is okay. All these challenges are there, should be there, or the challenge should be computed. And then the second phase is okay. We have all these challenges, and each one generates the proof. Once you have the proof, it's very much the same. You get some reward if you are included, maybe some penalty if you don't include it, or it's an invalid subproof, and of course the verifiers receive the proof. And in the last state, well, probably all of them can aggregate the proofs. And the interesting thing here in this step is that okay, you probably get a reward for submitting this final proof, and this is all of them. But you can also get a reward for your previous subproof being used in the last proof, and for also reward for using somebody else's proof on this proof. Okay, so the idea is that you can have a system where you are incentivized to use the other's one, and in order to get the proof. Of course, it can be a step 3B or 3C, that this is you don't get an proof in there. You can extend the time period, maybe with lower incentive, so that you can create. This is a simple example. I'm not saying that this is perfect. This is just an example of a protocol for generating a proof in a decentralized manner. Okay. Of course, you can combine this proof. I mean, you can have maybe, okay, the one that's gets the proof and the other gets the, you can do incentive for a verifier if you submit the full proof, and then this decentralized way of building the proof. As I mentioned, I think this kind of protocols has a lot of advantages. ZisK is prepared for this decentralized way, and I think that this is the way to go. I think I want to avoid having centralized actors with big clusters running that are necessary to run the network. And that's very much what I wanted to talk about. Thank you for listening, and I'm up for questions.
Thank you, Jordi. Great lead into the panel discussion. So, a couple questions here. Very quickly, what do you think of Jolt?
Well, Jolt. I mean, I have not like deep detail how it works. I know that's something about elliptic curves. I need to check. But what the few things that I read is that the interesting part of Jolt is these big lookup tables. I think this is something super interesting. But with Starks, we have this lookup idea, and we can do things very, very, very similar. So when I see the results, I will believe. I mean, I think it's great that there's people trying, and we will see. At this point,
sure.
There is nothing.
A good lead into the next panel. So are you considering launching a token for the distributed proof generation? Right answer. What challenges did you experience running setting up the on-prem proving cluster?
Well, was fun. I mean, the first, well, a lot of.
Would you be willing to speak at an ETH call
look,
on gray market GPU procurement?
Look, I can tell you that as an anecdote. I mean, just as a small story, but I bought all these GPUs in Switzerland, and I went to Girona. I mean, went to Spain, and I just took the furgo of my brother. And when I was in the customs, I was just okay. I don't know what's going to happen when they see me with all these things. So I was a little bit scared on that. But that's, I mean, we learn a lot of things about powering, about ACs, about electricity, how to run, how to manage. We learned that the providers, I mean, the GPU providers are really bad. The fact that NVIDIA don't sell gaming machines to the big cloud systems is bad. It has been a real pain, and actually building the best thing, I mean, is the Girona was run. I mean, we built it and was running perfect in the first, very much in the first.
Yeah.
The going with the cloud, having to, I mean, things running on, I mean, we saw clouds limiting the power of the GPUs just to save some money there, or running on top of Dockers, and I mean, very strange things that you don't have control. Sometimes, I mean, your software is not perfect, and you need to debug, and you cannot trust the hardware. This is a pain. So we learned a lot on that, and I think we got a very, very, very good experience.
Great. So stick around the stage. You're on the next panel. Feel free to bring the chairs up. And so, yeah, I'll give them a second to kind of swap that out. But I wanted to say some thanks. This is the last panel, and this whole event has really been a group effort and required a lot of effort on behalf of a lot of people. So I'd first like to thank the DevConnect team for putting up with a very stressed out, neurotic version of myself. And also to all the dozen or so researchers that reviewed all the speaking applications and really worked on synthesizing the agenda and making sure that they're prescient, timely topics that you guys would all speak about. Specifically, Sophia, shout out, really kind of helped crystallize the whole agenda and schedule. And obviously all the speakers and the teams that, it was a very, very large ecosystem-wide effort to put this together. Very pleased with how it came out.